Thanks for the opportunity to talk to you guys this morning. I'm largely going to talk about work we did in the Motueka Integrated Catchment Program between 2000 and 2010. The organisers asked me to talk about two things: the importance of sediment and then the ICM program itself. I'm not going to say very little about the importance of sediment because there are people in the room who are far more qualified than me to talk about the ecological impacts of sediment. Other than to mention that when we talk about sediment, we're talking about a wide range of particle sizes. So they have different sources, they have different transport pathways, they have different effects. So we've got everything from fine clay through to boulders. So when we're talking about sediment, we need to be quite clear about which part of the sediment continuum we're talking about. So it has a range of impacts, both in fresh waters and coastal waters. I guess the first one is sediment leads to a decrease in, increased sediment leads to a decrease in water clarity, which affects any organisms that rely on site to see what they're feeding on, both in freshwater and coastal. And then you get sediment deposited on the bed of a river or as a coastal environment that can smother the substrate and have serious effects on ecology again. But there are people here who talk on those effects much better than me. So given the shortage of time, right, so just to quickly summarise what we did in the Moderated Integrated Catchment Management Program, it was a 10-year program that took a ridge stops to the sea approach and tried to link together what's happening on the land with what's happening in the rivers and at the coast. So pretty similar to what the aim of the Moderated Catchment Collective is in many respects. And I've used that if this group had been operating at the time the program had been operating, it would have been a very rich relationship between community and science. It hasn't quite worked out that way, but nevertheless. But what we did in that program was we measured suspended sediment load at 7 sites for 7 years. Those sites were designed to cover the major variation in rainfall and rockfall across the catchment and the variations in land use as well. So the sites included Upper Motueka, Gorge, Motupico, Wangapeka and Woodman's Bend, which characterises the load into the Tasman Bay. In terms of deposited sediment, we measured the space and temporal pattern of deposited sediment at 30 sites for 6 years. And in terms of that work, we took a longitudinal transect up the catchment and the major tributaries, and we sampled upstream and downstream of confluences so we could see what impact input of sediment from different rivers was having. In terms of bed load, we use long-term cross-section data that goes back to the 1960s in this catchment, along with short-term GPS surveys that characterise the bed of the river in a lot of detail to assess changes in channel form, which reflect changes in bed load stories in the river system. We tracked sediment out in the coastal zone because that was one of the clear drivers at the time of the program when there was a lot of discussion about agriculture management areas off the mouth of the Motueka and the Rockall River. So people were particularly concerned about the impact of the river in those areas, potentially zoned for agriculture. That work was largely done by the Horseman Institute. And we looked at the ecological effects, particularly in terms of trout and scallops, because at the time there was a lot of talk about the impact of sediment in the Motueka River, which is internationally renowned for its trout fishery. There was a strong perception that the trout fishery had declined and the cause was sediment coming from forestry. So we tried to address that issue as best we could. And we also grappled with the scallop question where for many years people harvested scallops out in Tasman Bay, effectively with no harvesting any longer. And sediment again has been implicated in the decline of that fishery, and again forestry is a major source of that sediment. Right, so just in terms of results, this is going to be very much once over lightning, but please feel free to question me later on if the things you don't understand. But the first thing to say in terms of suspended sediment load is sediment yield in this area is very low by New Zealand standards. If you compare it with the east coast of the North Island, the west coast of the South Island, the rates of sediment yield are incredibly low, and it largely reflects the geology in this part of the country, which is particularly stable. The dominant influences on sediment yield are rainfall and rock type. I guess that's a bit of a global New Zealand-wide overview, but it applies in this catchment as well. Rainfall is a key driver, whether it's annual rainfall or storm rainfall. And we'll talk in a minute about the importance of storm rainfalls and flows. Slope and land cover land management tend to be secondary influences on the rates of sediment yield. Can be locally important, but tend to be in the whole catchment context a second order effect. Probably the most interesting thing we found out in terms of the suspended sediment work is how much large storms dominate sediment load. Some of you will probably remember the storm in Good Friday 2005 in the Upper Motueka and Motueka catchments, 15-year plus event probably. The roads were closed for a few days and quite a lot of landsliding and gullying in a number of parts of the catchment. What we were able to do though was demonstrate from suspended sediment yield measurements how in the area that was affected, which was basically up in here and in here, this area here, the sediment load in that area increased following that storm by a factor of about 10 to 20. As measured at Mock Gorge and Rock Creek, it went up by about 4 to 5 times. And that sediment load slowly reduced as time went by, but at the end of 7 years, the load at Mock Gorge was still elevated above what was prior to that event. Down at the coast, sediment yield at Woodman's Bend, the delivery to the coast, increased by about 3 times during that event. But after the 7-year period, from memory, it was largely returned to pre-storm levels. But those large storms dominate sediment load. In terms of sediment transport, it tends to be the 90, 10, 80, 20 rule. 80 to 90% of the work is done 10 to 20% of the time. And those storms have a persistent effect in terms of the length of time that they affect the catchment, but also how they can increase the load locally. What we found with respect to forest harvesting is we had the 4 main catchments that we were monitoring. We had 3 smaller ones where we were trying to tease out the influence of forest harvesting. What we found with respect to forest harvesting was that it produced a short-term localised increase in sediment load. So sediment load goes up by something like, well, in our case, about 5 times. We didn't have any major storms that affected that area, so you'd expect it would increase more than a major storm. But the more interesting thing with respect to forestry is that it recovers quite quickly. So within about a year or two, you tend to be back to pre-storm sediment. So it's, in terms of the influence, the large storms dominate much more than changes in cover due to forest harvesting and so on. One of the things, well, just in terms of the map, that shows the pattern of suspended sediment yield as predicted by a model that was developed for the whole country. And you can see that surprisingly the highest loads are largely in what's inventory gravel terrain and up here in sort of in the western side of the Red Hills. One of the other things that we were able to do, because while we only measured for 7 years, we were able to use the long-term flow record at Woodstock, which goes back to 1960, to produce a long-time series of annual sediment load, and it's incredibly variable. So it has ranged from less than 50,000 tonnes in a year to about 1.7 million tonnes. And you can see we were measuring during this period here, and the annual sediment load was actually really low during the period we were measuring. And you can see the big years were 83, some of you will probably remember that, and 74. So they produced massive amounts of sediment because of the number of storm events that occurred in those years. But you can see in terms of the trend line, this is a 10-year running movement. You can see that sediment load has been tending to trend downwards for there may be a variety of explanations for that. Right, so that's roughly what we found out in terms of suspended sediment load. When it came to deposited sediment, I guess what a lot of people had seen in the Motueka was big slugs of granite sitting near the river, and they look like they have a terrible impact on the river, particularly in terms of the trout fishery. What we found at our sites was that at most of them, deposited sediment abundance was really, really low. It's a very clean river by and large. I think most of you have looked around the rest of the country recognise how clean the waterway tends to be. The only exception to that was small tributaries on the separation point granite, so the likes of the Double and the Orinoco have massive amounts of coarse sand on the bed of those streams. The interesting thing about that in terms of influence in the mainstream of those rivers is that we could see no influence of deposited sediment being delivered out of those small tributaries of the mainstem waterway and causing an increase in deposited sediment in the mainstem. So most of our sites had no change in deposited sediment abundance over time, with the exception of the gorge, with that large flood in 2005 caused a short-term increase in the amount of deposited sediment. It was still quite low by New Zealand standards, but it was statistically significant increase. It only lasted for about a year or two. And we saw the same at our Wangapeka site when Newport's block was harvested at the confluence of Wangapeka. There was a short increase in deposited sediment, granite sand, but considering the amount of landsliding that occurred in that block, I was surprised how little deposited sediment increased at that site. The other thing we found that there was little relationship between the deposited sediment abundance and trout abundance, both over the period of our measurements, but also in the longer term. The trout abundance data is information that fishing game was collected over a number of years in the waterway. Initially, they had one side and then they put in the whole of expert science for measuring trout abundance, trying to tease out the relationship between variation in trout numbers and what drives that. And we in particular, looked at what might have caused the crash in the trout numbers that appeared to occur around 1995, or at least between drift dives that occurred out in 94 and 96. And what the analysis that we did showed was that it looked like the major driver for that was not sediment, but it was flooding. Not large floods, but small to medium-sized floods at the time of the year when the fry were emerging from the bed of the river. So it was flooding more than sediment. It was a major driver for that crash in the trout numbers. Right, in terms of bed load, as I said, we examined this in two ways using the long-term cross-section data going back to the 1960s, but also a series of detailed GPS surveys on an annual basis where we teased out both the spatial and temporal patterns in much more detail. Interesting to note is in the lower Waterway and Tapawera areas, we've got a lot of sediment in storage. The channel has been narrowed by river control work through the years. So in the Tapawera area, I think the average reduction in channel width since 1960 was something like 30%. So when you narrow the channel down, you provide more transport capacity, which tends to drive sediment mobilisation. What we derived from the GPS surveys was that the patterns of sediment or change in the riverbed are incredibly detailed and complex. So the diagram shows that we had three sites, one above the Motupico confluence, one is the Motupico itself, and the other is below the Motupico confluence, just upstream from here. And you can see the lines across here are cross sections that we derive long-term estimates of channel change from. And you can see that they don't very well. You can see that the colours blues are where the riverbed is raised, and the reds where it's degraded. And you can see that there's a really complicated pattern in all of these and all of its sites. And so both the cross-section data and the GPS surveys suggest that the channel overall is degrading. So gravel was being exported out of all three reaches. No, two of the Motupico, I think, had net degradation, but two of the three are degrading. And there's probably a number of different reasons for that, which we'll perhaps talk about later. But what it did tell us was that using the cross-section to characterise long-term channel changes, what was good at the time, there's much better ways to do it now with GPS or LiDAR, and you can really start to understand how the riverbed is changing in detail. The link with gravel extraction is a bit more complicated. there's always been a limited amount of gravel available in the river, which is allocated by TDC for extraction. At one stage, they were extracting over 100,000 cubic metres a year out of Motueka. And I think even when we were doing this work, they were still extracting around 10,000 cubic metres. We couldn't be clear about how closely the changes in the riverbed were linked with gravel extraction. Other than that, this site, this one up here, TDC had run a experiment here where they extracted 12,000 cubic metres of gravel off the wall for 3 beaches, just up the low tap area here. And I think people expected some pretty dramatic changes in the riverbed as a result of that, what appeared to be extraction. We couldn't demonstrate any significant changes as a result of that. So the length of gravel extraction is still a bit of a question mark in my mind. What do we find in the coastal zone? Well, this is probably one of the most interesting things that came out of the program. That effectively, what we suggested was the catchments needed to be redefined to include the coastal zone. Catchment is defined as an area on land which is topographically bound by the flow of water, but once it gets into the coast, it's a very different thing. But it's still the same link between what's happening on the land, what's happening out in the sea. It's not fixed by topography. It's fixed by what's happening with the flow in the river, the tides, and the wind. So that zone of influence from the Motueka River can extend up to 5 kilometres offshore and over an area of 180 square kilometres. The diagram just shows some work that was done tracking from the Red Hills here, where you've got ultramafic rocks with high levels of heavy metals like chrome and manganese. Hawthorne did some work tracking that sediment in the 2005 storm down the river and then out to the coastal zone. And the hatched area up there shows the zone of influence of those heavy metal rich sediments, which is quite small compared to the wider influence of the plume of the water, mainly because that rock produces coarse sediment probably settled out quite quickly close to shore, because in a big storm you can see the plume from Motueka extends all the way up to Tonga Island. So it's quite a profound influence. In terms of the scallop fishery, we didn't do a lot of detailed work here, but what we did do was just look at the records of scallop catch and look at the records of annual sediment delivery, and certainly the scallop fishery declined at a time when the sediment load into the bay was quite low. I don't doubt that the decline of scallop fishery is probably due to sediment, but I don't think it's due to current sediment. I think it's a cumulative effect. Probably going back to when the catchment was cleared. Some of you will probably recall that in 1877 there was a massive flood in this catchment. It's probably still affecting to this day. It's one of the potential reasons why the bed levels are still degrading. After that storm, there was massive aggravation in the catchment, and we were slowly adjusting over decades and centuries to that increase in sediments. So those are some of the takeaways. So everything I've talked about has largely been published, either in peer-reviewed scientific literature or contract reports. There's a report on the Motueka Rock catchment summarising what we knew before we started the ICM program, and that Journal of Marine and Freshwater Research summarised some of the key papers that were produced as part of the program. And it still has a website, so if you're interested in the program and what we do, you can go and have a look on the website.
Thank you. Take a question. Yep. Just put up your hand and wave at Les if you've got a question or a comment.